Lab 3, Black Hole. Can we examine the motion of an orbiting star and use it to calculate the mass of a black hole? The purpose of this lab is to use our observations to explain and quantify interactions and use those interactions to build an understanding of our universe. We've been given some information here, and using the mass of our star and some position data, we're trying to find the mass of the black hole that's causing the motion of the star. So we can see here that my star is accelerating around some object that we assume to be our black hole. It's changing its direction or the magnitude of velocity, and we know by Newton's second law that that must be caused by a force. This force equals mass times acceleration. We can say that also force equals mass times the change in velocity over the change in time. We can use all these positions here to find v and delta v and F net, but that only works if we use a relatively small delta t and we assume a constant force for that moment in time. However, to be able to do this at any moment where our forces change constantly, we need to do some calculus. We can use calculus and Newton's second law to break up the net force into parallel and perpendicular portions. Calculus likes to take us to a limit, and we're going to try to get as close to that limit as we can by using a relatively small delta t to approximate the magnitude of F net parallel. We can see that magnitude is equal to the magnitude of the change in momentum divided by the change in time. We can also use our net force to find the perpendicular portion by adding them together. We can see these forces here in the model. We've got my F net is the red arrow, F net parallel is the black arrow, and F net perpendicular is the blue arrow. The second main concept that we're going to have to understand is the law of universal gravitation, which states that the force of gravity is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the two objects squared. And the direction of the force is going to be on a line between the two objects attracting one another. So now we have to plug those concepts into our model. We're using the LEN function to calculate between two successive values in our CSV file. This helps us find values such as velocity, momentum, and changes in these values. Now we come to Newton's second law. We use this to calculate the force on our object using the change in momentum divided by the change in time. We've got the parallel portion of the net force using the change in magnitude of our momentum. This tells us if our object is speeding up or slowing down. We get our perpendicular portion by subtracting the parallel from F net. This tells us how much our object is changing direction. Finally, we use the law of universal gravitation to solve for the mass of the black hole. You can see the results of these calculations in my output window here. We have the time, the magnitude of the net force, and a consistent mass of the black hole at 1.981 times 10 to the 31st kilograms. Let's find out about our forces using data from our CSV file. We can calculate two velocity magnitudes based on the difference between three successive position magnitudes, then dividing by our delta t of 86,400 seconds. We can check our calculations against the model data, and we can see that we have the same values for the magnitudes of the velocities. We can use Newton's second law to calculate the magnitude of F net parallel using the mass of the star and the change in the magnitude of the velocity. We can then use the net force data from our model to find the perpendicular portion of the net force. And here we can see these values. We know that at this moment my object is speeding up and changing direction. Now we can use our force data along with Newton's law of universal gravitation to calculate the mass of the black hole. We know the magnitude of our net force, and we know that this is coming from gravity. If we plug in our data using the position vector that corresponds to our force as r, we can calculate the mass of our black hole to be 1.981 times 10 to the 31st kilograms. A great way to check this answer is by plugging the mass into a different r position and seeing if the magnitude of your calculation matches the model data. So without using a computer model, it's still possible to find a close approximation for F net. To do this, use vector calculations from the given star positions, but be sure to keep all vector values as vectors. Do not use any magnitudes. We can use Newton's second law, and then we can use the law of universal gravitation to still come up with an answer. My answer, I got 2.01 times 10 to the 31st kilograms, which was 1.6% off the model's calculated mass. So it's not perfect, but it gives you a good idea if you made your model correctly. So how are the F net values different from the delta P over delta T values? Well, the F net values are total vector forces with magnitude and direction. In this case, they'd be in line with the two objects pulling them together. The parallel portion is in the same direction of the velocity, which determines if the object will speed up or slow down. The perpendicular portion is at a right angle to the velocity, which tells the curvature of the trajectory. The delta P values are all values calculated from observations. They are a result of the forces above. We can approximate the corresponding forces from these values, but we need to use a small enough delta t for the approximations to be reasonable. So if we put in a new black hole with a different mass, will we get the same data? And no, this can't happen. We can use Newton's law of universal gravitation to demonstrate this. If we use the same value as r, but then we change the mass of the black hole, we can see that we get two completely different force values. Since force equals mass times acceleration, this would cause different acceleration and therefore a different set of positions. However, if we use a larger delta t, our precision would be reduced and we would likely see a slight variation in mass calculations. We used observational data to interpret and understand motion, build a model, and calculate the properties of a dynamic system. Using Newton's second law, we were able to understand the changes in magnitude and direction of the gravitational force. Using the law of universal gravitation, we were able to calculate the mass of our unknown, and our black hole mass is 1.981 times 10 to the 31st kilograms.